We're in section 5.2, monotonicity and concavity. This is a long one. We'll have 2 videos on this. There's a lot of stuff in this, but there's also a lot of applications, both in mathematics. We understand the behavior of a function based on the rates of change. And that implies that not only can we sketch the curve and understand things mathematically, but also there are lots of applications scientifically. Anytime you know when the rates of change equals 0, when there are maxes and mins for a function, there are all sorts of applications for that. Predator-prey models, population models, all sorts of things. So anyway, last time we focused on absolute extrema over an interval. This time we're going to go back to local extrema, right? Local maxes and mins, right? Things like this or like this. And in particular, we're going to learn how to determine them. Now, first off, remember the derivative is the rate of change of a function. So if the derivative is positive, then there's a positive rate of change, and the function is increasing. Similarly, if the derivative is negative, then there is a negative rate of change, which means the function is decreasing on the interval. So using this, we are going to learn the first derivative test. You don't need to memorize the statement of it, but you do need to know how to use it. If we have a critical number of a continuous function, remember, critical number means that our derivative either equals 0 or does not exist at c. Then if we have a function, right, and f prime changes from positive to negative, so we have an increasing function, and then at c we have a decreasing function, well then what does that mean? We have to have a local maximum at c. In other words, f of c is a local maximum. If the opposite happens, if we're decreasing before c and then increasing afterwards, well then we've got to have a local minimum at c. So f of c is a local minimum. And if f prime doesn't change, if we have something like this, where maybe we're kind of going up, well, let me do that a little bit better, or maybe increasing, and then we're 0 right here, we're derivative 0, let's say, and we continue to increase, or maybe the opposite happens, we're decreasing, and then, our derivative is 0 for a second, then we continue to decrease, but we have a, f prime of 0 right there, then we have neither, and f of c is a saddle point. I think I defined that last video, but just as a reminder. Right? You don't need to know that term, but just good to know it. Anyway, let's do an example. We have a function, it's a polynomial. Find all intervals of increase and decrease, and find all local maxima and minima. And by the way, when I say find all of them, I also mean find and classify them. So like state whether the local maxes and mins, okay? I'll leave a little space for later just if we can maybe try to graph the basic shape of the curve. Anyway, here's how we're going to approach this. Find f prime of x, find the critical numbers. All right, in this case, that's going to be 3x squared minus 14x plus 8. I think it's going to exist everywhere, right? It's a polynomial. Derivatives always exist. So we set it equal to 0. We do a little bit of factoring. We get 3x minus 2 times x minus 4 equals 0. Checks out. And so that means that x equals 2/3 and 4. So these are the critical numbers of f. These are the numbers where the derivative equals 0. All right, so now we're going to just set up a little interval like this. I'll call this f prime right here. And we're just going to mark 2/3 and 4. It doesn't need to be super to scale, but whatever. Try to make it ish to scale. All we're going to do is we're going to find where the derivative is positive and where the derivative is negative. Now, here's the cool thing. In order to do that, all you need to do is plug in 1 point anywhere on this interval, any number less than 2/3, and plug that into f prime. And if the derivative is positive, then the derivative is positive on that whole interval. If the derivative is negative, then it's negative on that whole interval. So if we plug in, what would be an easy number to plug into f prime? 0 is the answer. I think 0 is the easiest thing to plug into f prime. You get 8, which is positive. So I don't really care what it is. I just care that it's positive. So f prime is positive on that whole interval. Next up, what's an easy number to plug in on this interval right here? That would be 1. Plug 1 into f prime, and we get 3 minus 14 plus 8. That is negative. So f prime is negative. And then last but not least, plug in a value, I don't know, like 5 or something. Oops, sorry, that should be f prime of 5. And you'll just see it's positive, so we're increasing. So we have the intervals of increase and decrease, right? Wherever there's a plus, f is increasing. Wherever there's a minus, f is decreasing. Because plus means f prime is positive, so it means f is increasing. Wherever there's a minus, f prime is negative, which means f is decreasing. All right, so anyway, let's answer the question. By the first derivative test, I'll abbreviate it as FDT, f has local maximum f of 2/3, which equals, I don't want to simplify it, but it's 2/3 cubed plus, what was that, 7 times 2/3 squared plus 8 times 2/3 plus 16. Yeah, all that. And local min, f of 4, which equals, I don't even know, 4 cubed plus 7 times 4 squared plus 8 times 4 plus 16. Remember, to find the local max and the local min, we use the first derivative test. But the actual local max and the actual local min is the critical numbers plugged into f, right? Local maxes and mins are y values, okay? Okay? So those are the local maxes and mins. Also, we should say f is increasing on the intervals with the plus signs. So we write negative infinity to 2/3, and then we write a union 4 to infinity. That's the notation. And f is decreasing on the interval 2/3 to 4. Okay? So one last thing I want to do is I want to just duplicate this real quick, just take it up here, and just kind of, I don't know, just use it as a little guide to sketch the curve. So if I go ahead and take some axes and something like this, and I want to just try to basically sketch the curve. We'll have 2/3 over here. I guess it's somewhat to scale, maybe a little bit over here. It's like, yeah, this is 4. The function does something like this. Looks like it goes, well, actually, let me use red for the function. For this curve, right? So the function looks like it does something like this, and then it goes down, and then it goes back up. Something along those lines, right? Now, if you think about it, it's a cubic. If you know how a cubic behaves, you know it's something a little bit more like this. But how do we know exactly the curvature of the curve? Well, we'll get a little more into that next time. Anyway, let's do another example, all right? We have another function, same thing. Find all intervals of increase and decrease, and all local maxes and mins, okay? Well, critical numbers, we're going to have f prime of x equals, so a little more annoying, right? We have to do a quotient rule. I don't think it's too bad, right? Low d high minus high d low all over low squared. Now, here you need to be a little careful. Anytime you have a fraction with x's in the bottom, you have to worry that the derivative maybe doesn't exist. But the bottom is always greater than 0, so we never actually have to worry about f prime not existing. We just set this equal to 0. But let's simplify this a little bit. We're going to get x squared plus 1 minus 2x squared all over x squared plus 1 quantity squared. And if we simplify this, we're going to get 1 minus x squared all over x squared plus 1 quantity squared. We're going to set this equal to 0. Now, here's the cool thing. When you have a big messy fraction like this and you set it equal to 0, the bottom can never equal 0 in this case, right, because it's greater than 0. So the only way to make this fraction equal to 0 is if the top is equal to 0. So just multiply both sides by the bottom and don't even worry about it, right? Just say, okay, 1 minus x squared equals 0. And this implies 1 minus x times 1 plus x equals 0. If that factoring is weird to you, write it as x minus 1 equals 0. Okay, anyway, this is x equals 1 and negative 1. And we have, yeah, those are critical numbers. So now we're going to draw an interval. So again, we have our f prime, we have our negative 1, we have our 1. And we're going to go back to f prime. Now be a little careful here. Make sure that you have f prime before you've changed it. So this was our most simple form of f prime. Let me just maybe write it over here in blue. F prime of x equals 1 minus x squared all over x squared plus 1 quantity squared. Okay, so we'll plug something into here. Maybe plug in, I don't know, negative 2, right? We see that the top is going to be negative. We're going to get a negative over, well, I guess the bottom is always a positive, so we have a negative. So we have negative here, right? If we plug in 0, I hope you see we're going to get a positive, right? It's 1 over 1. And if we plug in a positive number, we're going to get, again, I don't know, plug in 2. We're, again, going to get a negative over a positive. So you negative. Okay. So that's what we have. Okay. So now to answer our question, we say by the first derivative test, f has local minimum f of negative 1, which equals, and this is not so bad, we can actually do this out. It's going to be negative 1/2. And local maximum f of 1, which equals, I think it's positive 1/2. F is increasing on negative 1 to 1. By the way, we always use open intervals. And decreasing on negative infinity to negative 1, union 1 to infinity. Okay, so we answer the problem. Now, if we, again, I'm gonna go ahead and duplicate this just so I can get, I'll shrink it a little bit, just so I can get an idea of what the sketch of this curve would look like, right? And so if we do this one out, we see our function is, I guess if negative 1 and 1 are points of interest, we see, okay, our function is maybe decreasing and then increase. Maybe that's a little much. Maybe it's like decreasing and then increasing and then decreasing again. Maybe it looks something like this. Now, it turns out, if you actually sketch the curve, it's really doing something like this. Let me make sure I got this. It's really doing something like this. Actually, so I guess we know a little bit more than that because we did have our critical points, right? We did know that we had, well, one sec. We did know that we had here, this is negative 1/2, and this is positive 1/2. So we did know that we had this point and that point. So I guess we knew that we had something like this, and then maybe this, and maybe this. But it turns out, actually, we really have this. something close to that. Down here. That's actually what we have. In particular, the long-term trends are different from what you might have thought. You can't really use first derivatives for that, but we have second derivatives and limits at infinity to see how that works out. But just to point out, first derivatives don't tell us everything. Okay. So anyway, let's just look at another. Just take a little digression here, and let's look at something else, right? We've been using first derivatives to figure out a function's local max and min. Okay? Let's go ahead and take the second derivative of a function. All that is the derivative twice, the derivative of the derivative, right? So we say dy over dx equals 4x cubed minus 4x. The second derivative would just be d squared y over dx squared, and that equals 12x squared minus 4. Okay. So for polynomials, it's not so bad. The function kind of gets smaller and smaller. For trig functions, let's see what happens. The derivative here is going to be cosine of x. I guess that's plus sine of x. Here, the second derivative, denoted f double prime of x, equals negative sine of x plus cosine of x. So I don't know if you really say this is bigger or smaller. It's the same kind of absolute value, so to speak. And then sometimes if you have something nasty like a product, well, the second derivative gets a little yucky, right? Here we have a product rule, right? We have secant of x plus x plus 5 times secant of x tangent of x. Right, maybe I'll just erase this guy. But so to take the second derivative, right, to take the derivative of the derivative, right? Nothing terrible, but we have a double product rule. And so it winds up being 1 times secant of x tangent of x plus x plus 5 times secant squared of x tangent of x plus x plus 5 secant cubed of x. Gross, right? Sometimes it's just, there's just no nice simplification, or it just takes a while. Okay. Now this is very, very important. The second derivative measures the rate of increase of f prime. It measures the acceleration of f, right? If you think about it, the acceleration of a function is the rate of change of the rate of change. Okay. Now there are four curves that we want to consider in this situation. 4 maybe situations that we want to consider. Let's go here and here. So case 1, we have f prime is greater than 0 and f double prime is greater than 0. Here, the velocity of a function is positive and the acceleration is positive. So the derivative is getting bigger over time. So we have something like that. What about the situation where f prime is positive, but the acceleration is negative? Well, our function is still increasing, right? Remember what we said at the beginning of our lecture. But it's slowing down. So we're increasing less quickly. So we have a curve like that. Now, if we have both the derivative and the second derivative less than 0, that's like slamming on the reverse pedal, right? We're going down. We're going down, and we're going down quicker and quicker. As opposed to f prime is less than 0, but f double prime, the acceleration, is greater than 0. Well, that's a situation where we're still decreasing, but less so. So we have a curve like this. And we want to remember these curves, okay? I'll go over them a bit in class, but we want to remember these curves. So anyway, one last thing I want to just teach us real quick is the second derivative test. If we have a second derivative continuous near a point C, then if we have a critical point C, right, f prime equals 0, and the second derivative is less than 0, then f of C is a local, what do you think it is? Turns out it's maximum, right? Because let's think about it. If we have a second derivative equal to 0, or sorry, second derivative less than 0, then we have one of these two curves. And if you combine those, if you just stick them together, you get this guy. Okay? And analogously, if we have a second derivative that's greater than 0 at a critical point, well, if you sort of flip-flop these curves and stick them together, you get this, which is a local minimum. Okay? So really quickly, let's maybe just do this guy real quick. Second derivative test, right? Find all local maxes and mins, right? So here we're going to do, take the derivative, set it equal to 0. We already know this, right? We're going to get this guy. Right, we factor it. We already know how to factor. And then we just take the second derivative. F double prime of x is going to equal 6x minus 14. And here we're going to do is we're going to plug in our critical numbers. Well, actually, let's do that in the next part, right? F double prime of 2/3 equals 6 times 2/3 minus 14. I think we can see that that's less than 0. Implies that f of 2/3 is a local max. F double prime of 4, meanwhile, 6 times 4 minus 14 is greater than 0, implies f of 4 is a local min. And this is by the second derivative test. Okay. Now note that this doesn't give us intervals of increase and decrease, but maybe it did take us a little bit less work than the first derivative test. Just want to point that out, right? All right. So anyway, just another super quick example, right? For this problem, we use the second derivative test. We get f prime of x. Remember that this is going to equal 1 minus x squared over 1 plus x squared quantity squared. Oh, wait, whoops, x minus 1? Hold on a sec, did I? Hopefully I didn't do the wrong, oh no, okay, sorry, this is a different problem. Yeah, let's actually go ahead and just do the problem that we had before. So I'm going to change this function to be this guy. Right? Do that guy. Okay. Sorry, we're gonna change that. Okay, so we have the same derivative equals 0 at x equals 1 and negative 1. All right, now here the second derivative, a little bit more annoying, right? F double prime of x is going to equal low d high minus high d low all over low squared, which is really going to make this to the fourth, right? And we could clean it up, and actually this is not quite as bad as it looks because we can cancel a 1 plus x squared factor from all that stuff. But anyway, for each critical number, right, you'd plug it in, right? So we would do f double prime of 1 equals, what is this going to be? 2 times 2 minus 0 all over 2 cubed, which is greater than 0, implies f of 1 is a local min. And meanwhile, f double prime of, oh, shouldn't it? I thought that was supposed to be a max. Did I mess something up there? Maybe not. I'll have to take a look at that. Anyway, f double prime of negative 1 equals, well, it's going to be the opposite, right? We're going to have a negative, right? It's 2 times -2 minus, and this will be 0 all over, and then this will be, again, 2 cubed. And this is less than 0. So it seems that f double prime, or sorry, f of -1 is a local maximum. Let me just double check that, because I think we should be getting the opposite. Oh, yep, that's why. Low, d high, this should have been a negative. Yeah, sorry. Okay, so then that makes more sense, right? That means this is 2 times -2. And we just flop this. And this is 2 times +2. Sorry about that. So this is great. Okay, perfect. Good. So needless to say, sometimes the second derivative test is a bit easier. Sometimes the second derivative test is a bit harder. And that's all we've got for today.